So it turns out that functions are not only very, very cool to play with, but they also can be operated as though they're just numbers. Seriously, as though they're numbers. Let's have a look. Well, a function we know is something that looks like this. F of x equals x squared. That's just a quadratic function. No big deal. But g of x, a different function, could be, let's see, 3x squared plus 2x. That's a different function. Not a problem. Check this out. If I decided that I wanted to add these two functions together, because that was my hypothesis at the start, that functions can be operated like numbers, and one of the things that we do with numbers is we add them. If I wanted to add f of x plus g of x together, what would I get? Well, f of x is really just x squared. And g of x, well, I'm going to add that, is really all of this. So if I substitute that in for after the plus sign, instead of a g of x, I put in 3x squared plus 2x. That's just another function. I can simplify it, and I should simplify it. That would be 4x squared plus 2x. I could choose to factor the 2x out, or I could choose to leave it like this. They're equivalent statements, and they flip back and forth so easily. You just make your own choice. How do you like to look at it? So what I've done is I've created another function, h of x, by adding two other functions together. Well, what about subtraction? Well, obviously we can do it with subtraction because addition and subtraction are the same thing. So let's just do it real quick. Let's let p of x be the f of x minus the g of x. Well, that's exactly what I did up here, except I'm going to have to use parentheses and a minus sign and do a distribution. So f of x is x squared minus contained 3x squared plus 2x. And now that minus is going to have to distribute, which changes all the signs inside, and then I can simplify. So x squared take away 3x squared is negative 2x squared minus 2x. Give me a second. Yep, just thought I'd check my work real quick. Okay, I have added, subtracted. What's another operation? Multiply. I have multiply. So let's say q of x. Is it possible to write the q of x equals f of x times the g of x? Well, that's a duh, because the f of x is just x squared, and I'm going to multiply that by 3x squared plus 2x, totally allowed, and I end up with 3x to the fourth plus 2x cubed. And again, I can either factor or not factor, just depending on whatever I want it to end up looking like. So what about division? Well, p of x, or I use p of x, let's use d of x. Let's see if I can divide f of x by g of x. Let's see what happens. Well, f of x is x squared, g of x 3x squared plus 2x. Okay, in this case I don't really have a choice about factoring because I want to cancel any common terms and write this in the most reduced form. So x squared over x times 3x plus 2. I can cancel one of the x's and I'm left with x in the numerator and 3x plus 2 in the denominator. Now, we have to be uber cautious right here because we're dealing with a fraction, which means I have to be concerned about not having a 0 in the denominator. So I have to automatically restrict that g of x is not equal to 0. So if g of x is not equal to 0 over here, I'm working to say that g of x, well here, g of x is not equal to 0 because 3x squared plus 2x is not allowed to be 0, and so x is not allowed to be 0. So I'm saying the same thing in both cases, in both situations in this case. So these are called combinations of functions. And all I've done is combine two functions over one of the basic operations. There is a notation change, so even though you can write f of x plus g of x, there's another way to write it, and you should recognize that just as readily as you recognize this notation. So let's go ahead and write that out. The sum notation looks like f plus g of x. So you're adding the f and g functions in the variable of x. And that's just the same thing as f of x plus g of x. The difference, same thing. I could actually say sum and difference. All right, so I'd make that a plus or minus. Little shorthand there. Okay, and then for multiplication, of functions, I would write the f times g of x and then for division, you guessed it, the f divided by g of x. So these are equivalent statements. This sum and difference is equivalent to the f of x plus or minus the g of x. It's just a little bit shorter to write. And the f times g of x is equivalent to the f of x times the g of x. And the f divided by g of x is the same thing as the f of x divided by the g of x. Okay, so that turned out to maybe not be quite as exciting as I sold it in the beginning, but the next concept is totally cool. So these are combinations of functions that we talked about. There's another thing called the composition of functions. All right. Composition of functions means you can function a function. And it definitely does not get much cooler than that. So let me show you. We'll start with an example. If I have an f function equal to 2x squared minus 1 and a g function equal to x plus 3, I can actually put the g of x into the f of x. So I have the f of g of x, where I put the g of x inside of the f of x. So the f function is 2. So this x in the f function is where I want to stick in the g of x. So I'm going to make a big giant hole so I have room to put it and finish writing the rest of the function. So this is definitely the f of x that I have so far. But now instead of plugging a number like 2 or 3 or 4 in, I want to plug in x plus 3. Now I just have to simplify. That's 2 times, well, this is a binomial squared, so it's x squared plus 3 times x is 3x times 2 is 6x plus 9 minus 1. That's 2x squared plus 6x plus 18, take away 1 is plus 17. So this is the f of g of x. And it also has its own special notation. We say the f of g of x. And notice how it looks like fog. That's like a multiplication dot, only it's an open circle rather than a closed circle. So that's the f of g of x. Turns out you can also g of f of x. And that would be, let's do the same functions this time, and I find it's easier when I'm doing this to go ahead and rewrite it as the g of f of x. For me, it's easier to see that what I'm doing is plugging f of x into g of x. So I'm going to start with g of x, only where there's an x, I'm going to put a big open hole where I'm going to plug f of x in a minute, plus 3. Now I can put f of x in, so I get 2x squared minus 1. And this one simplifies much easier than the first function, or than the f of g of x. I get 2x squared minus 1 plus 3 is plus 2. So I get 2x squared, negative 1 plus 3 is plus 2. And so that would be the g of f of x. I think we'll do one more example. So in this case, I'm going to call the f of x the square root of x minus 1. And then the g of x is going to be x minus 1 squared. So first we want to find, well, let's keep our colors consistent. Let's find the f of g of x. Well, I like this notation better, so I'm just going to write it out again. And so now I see that what I want to do is write the f of x but leave room to plug g of x in. So I get the square root, that's going to be g of x minus 1. Now I can go ahead and plug in g of x, x minus 1 squared. And then I have to go ahead and do whatever simplifications I can. So under the radical, I have x squared minus 1 times x is 1 times 2, so minus 2x plus 1 minus 1 equals x squared minus 2x. And then I have to be careful about restrictions on the domain because I have to keep what's under the radical positive. And so in this case, I would have the domain is x is less than or equal to 0, because x can certainly be 0 because you would have a 0 in the radical. And then any value less than 0 would be good, because you'd squaring a value less than, a negative value less than 0 would be bigger than multiplying that same value by 2, and so you would get a positive number inside because you're subtracting a smaller number from a bigger number. And x would have to be, well, if I factored this, I'd have x, well, let's not factor it. X would have to be bigger than 2. Or equal to 2, because 2 squared is 4 and 2 times 2 is 4, and so anything bigger than that would give me a bigger number, take away a smaller number, and I'd be done. So the last idea is that sometimes you'll be asked to decompose a function. So decompose. And that's exactly what it sounds like. If composing a function is putting two functions together to create one, decomposing a function is taking one function and breaking it into the two functions that would have created it. So a good example of a decomposed function could be if h of x equals 3x squared minus 12x plus 12, you would want to factor out a 3, so you get x squared minus 4x plus 4. Sorry, I thought I copied it wrong for a second there. And then go ahead and factor x minus 2 squared. So we can call the outside function 3 times something squared. So we could say that this is that h of x equals f of x, f of g of x, where f of x, the outside function, is the 3 times something squared, and g of x, the inside function, would be the x minus 2. So sometimes you have to decompose functions, sometimes you have to compose functions in order to do various things with them.